Hello and good afternoon to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will discuss an important algorithm in operating system that is referred to as Dijkstra's-Bankes algorithm. Dijkstra's-Bankes algorithm is a deadlock avoidance algorithm that aims at determining allocation sequence of the resources to the processes in a manner that the system enters into a safe state, or in a manner that the system does not enter into a state of deadlock. So this is the objective behind Dijkstra's-Bankes algorithm. Again, I'm repeating it. Dijkstra's-Bankes algorithm is a deadlock avoidance algorithm that aims at determining allocation sequence of resources to the processes in a manner that the system does not enter into a state of deadlock. Now, before moving forward, let us discuss some of the important attributes of Dijkstra's-Bankes algorithm. Now, let us assume that there are m number of resources and there are n number of processes. So let us assume there are m number of resources and n number of processes. Here, m represents the number of resources, but it does not represent the number of instances of the resources. So here, m is just a representation of the number of types of resources that the system has in it. Taking these two considerations, let us discuss the attributes of Dijkstra's-Bankes algorithm. The first one is called as available m. Available m is a one-dimensional array of size m which indicates available resources that are there in the system. Available m is a one-dimensional array that indicates available resources that are there in the system. For an example, if available m is as 1, 2, 3 and 4. So it implies it has one instance of resource R1, two instances of resource R2, three instances of resource R3 and four instances of resource R4. So that is the way how available m is interpreted. So it indicates the available resources that are there in the system. Now the next is called as max nm. Max nm is a two-dimensional array of size m cross n. So it's a two-dimensional array of size n cross m which defines the maximum demand of each processes from each resource type. So it is a two-dimensional array of n cross m that defines maximum demand of each process from each of the resource types. Now you have allocation nm. Allocation nm is again a two-dimensional array of n cross m that defines the resources of each type currently allocated to the process. So max defines the maximum demand of each processes, whereas allocation defines the resource of each type currently being allocated to the processes that are there in the process set. Now need nm. Need nm is a two-dimensional array of n cross m that indicates the remaining need of each processes. So how many resources are now required after allocation by the processes is represented by need. So intuitively, if you think, need will be the difference of maximum and allocation. So need of ij is equals to maximum of ij minus allocation of ij. So need matrix will be determined as a difference of max and allocation matrix. So need is equals to max minus allocation. Now request nm is again a two-dimensional array of n cross m that indicates pending request of each process, right? Okay, so whatever is the pending request of each process is represented by request nm. So here now what we have is we have discussed 5 attributes, out of which one is a unidimensional attribute, that is available, and 4 are two-dimensional attributes of n cross m with their specified purpose. Now before proceeding on with the description of the Bankes algorithm, let us try and simplify the processes that are involved in performing various steps in Bankes algorithm. So for easing that, we will consider each of the rows in allocation, need, request and maximum as vectors. So here what we are doing is we are considering each of the rows in the two-dimensional array, which are allocation, need, request and max, as vectors. So here we will be performing comparison of vectors. So where individual rows will be represented as vectors. So here what I can do is I can define a relationship less than equals to between two vectors x and y, where x and y individually are of size n. So here what I'm trying to do is I'm trying to establish relationship between two vectors x and y, where x and y are of size n. Now let us try and explore the relationships. So the first relation is x is less than equals to y. So this implies x of I is less than equals to y of I, where I is from 1 to n, where x and y are vectors that represents individual rows. So here I've considered two rows. So one of the rows has value 1, 2 and 3. The other row has value 2, 3 and 4. So I'm comparing 1, 2 and 3 with 2, 3 and 4. So here I'm performing a vector comparison. Even though whenever vector comparison is performed, the individual elements are compared, but for simplicity of performing operations, so we are comparing it as vectors. So here 1, 2 and 3 is less than equals to 2, 3 and 4, because 1 is less than equals to 2, 2 is less than equals to 3 and 3 is less than equals to 4. So the condition holds true. So the first vector is less than equals to that of the second vector. Now likewise x is not less than equals to y. So x is not less than equals to y implies that x is greater than y. So for some I. So for an example, 1, 2, 6 is one vector, 2, 3, 4 is another vector. So 1, 2, 6 as a vector is not less than equals to 2, 3, 4 as a vector, because 1 is less than equals to 2, 2 is less than equals to 3, but 6 is not less than equals to 4. So that condition is not satisfied. So here this is the way how we try to establish relationship between the different rows that are there in the two-dimensional array. Now let us proceed on with the Banker's algorithm. Now the Banker's algorithm is detailed in 6 steps, right? Wherein the first step says that process Pi makes request for resources. Process Pi makes request for resources, and that request is represented as request of I, which is a vector. So let request of I be the corresponding request vector. So here request of process Pi is represented by request of I, which is a vector. So if P of I wants k instances of resource Rj, then request of Ij will have an entry k. So that is the way how the representation is made, or the way how the interpretation is done. So if P of I wants k instance of resource type Rj, then resource Ij will be equals to k. Now let us go into the various operations in the Banker's algorithm. If request of I is not less than equals to need of I, if request of I is not less than equals to need of I, which implies that request of I is greater than need of I. So if this particular condition exists, then there is an error, because it should not so happen that the request that is being placed forward by the process or by a process is greater than the need of that particular process. So this should not be true. So if request of I is greater than need of I, or if request of I is not less than equals to need of I, then there is an error. So what we need to say is we need to say that this particular condition should not exist, or there is an error. Otherwise if request of I is less than equals to need of I, then what we need to check for is we need to check for if request of I is not less than equals to available. So if request of I is greater than available, so whatever resource that is available in the system, if request of I is greater than that, then the process must wait. Right? So if the request of I is greater than whatever is available, then the process must wait. But we need to always ensure that request of I is less than equals to need of I. So if request of I is less than equals to need of I, but request of I is greater than available, then Pi must wait. If request of I is less than equals to available, that means request of I can be catered to by whatever is available in the system, then we'll proceed on with a sequence of steps. So what we'll do is we'll make available equals to available minus request. So whatever is available from that, we will substitute or we'll subtract the request. Allocation will be allocation plus request, because we are allocating the requested number of resources to the process. And need will be need minus request, because out of the total need now, the process will be requiring request less than what was actually needed. So that is the way how the operation is to be performed. So available will be available minus request, allocation will be allocation plus request, and need will be need minus request. Now once these sequence of steps are performed, what we need to do is we need to check for whether the system enters into a safe state. Only if a system enters into a safe state, then the allocation is proceeded with. Otherwise the process has to wait until unless the request can be catered to. So this is a very important step that the banker's algorithm performs. So it checks for whether the resulting state is safe or not. Whether the resulting state is safe or not, that basically means whether the system enters into a safe state after that particular allocation. If the system enters into a safe state after the allocation, then you proceed on with the allocation. Otherwise you need to make the process wait until unless the request can be catered to. Now here, in case of Dijikr's banker's algorithm, there is an additional safety algorithm that is checked when we proceed on with the allocation of resources to the processes, right? Okay, so now let us discuss the safety algorithm. Now the safety algorithm is a very simple algorithm. So here what we'll do is we'll consider two vectors, work and finish. Work and finish are two vectors of size m and n respectively. So work will keep track of the resources, whereas finish will keep track of the status of completion of the various processes that are there in the system. So the size of work should be m because there are m number of resources, and size of finish should be n because there are n number of processes. So here the first step says that initialize work to available. So whatever initialize work with available, so whatever is there at available will be placed to work. So work is equals to available, and finish of I is equals to false. So we are initially assuming that none of the processes are over, or none of the processes have completed its execution. So that's why the status of each of the processes is kept as false. So finish of I is false for all I. So initially what I have done, we have initialized work with available, and we have initialized finish with false for all I, assuming that the set of processes that are there in the system have not completed its course of execution. Now in step number 2, find an I such that finish of I is equals to false and need of I is less than equals to work. So now what we need to do is we need to find a process whose status is false, which implies a process that has not yet completed its execution, and then we need to check for whether need of I is less than equals to work. So whether the need of that particular process is less than equals to whatever is available. Now when this particular condition is validated, the consequence can be two. One is, if no such I is found, we need to perform a sequence of steps, and if such I is found, we need to perform a sequence of steps. So first let us consider that no such process is found. So if no such process is found, then go to step 4, which implies that there is no process which is yet to complete its execution, which implies that all the processes have completed its execution, right? Okay, so if no such I is found, then go to step 4. So we assuming, so if there is no such process in the system whose completion is whose execution is not yet complete, then it implies that all the processes have completed its course of execution. But if an I is found, if a process is found, where finish of I is equals to false and need of I is less than equals to work, then what we need to do? We need to allocate work to the process. We need to allocate whatever is available to the process. The process will complete its execution. Once the process completes its execution, it will deallocate the resources. Once the deallocation is done, then work will be updated with work plus allocation, because whatever was allocated is now released and the available resource has to be updated. So this particular statement, work is equals to work plus allocation I, is a consequential step. Before that, we will allocate work to the process. we'll make the process complete its execution, we'll make the process deallocate its resources, and then eventually we'll update work as work is equals to work plus allocation. So this is a very important step that all of us needs to understand, because here there are some sequence of actions that are hidden. The sequence of actions that are hidden are allocating work to the process, making the process perform complete its execution, then deallocating the resources, and then eventually updating work as work is equals to work plus allocation. So once work has been updated, once the available resource set has been updated, then what I need to do, I need to say that the process has finished. So finish of I will be initialized with true, and then we will go to step number 2, because I need to find another process that is wanting for allocation of resource, where finish of I is equals to false and need of I is less than equals to work. So this particular process goes on until unless all the processes are selected and the resource is allocated, and eventually when all the processes have completed its execution, finally the resource set is updated and the system terminates the or concludes its operation with the processes, right? Okay, so this is the way how the safety algorithm works. So in today's class, what we have learned about is, we have learned about what is Banker's algorithm, we have learned about what is the objective of Banker's algorithm, we have discussed the various attributes of the Banker's algorithm, we have discussed the types of the attributes of the Banker's algorithm, and we have also specified the purpose of each of the attributes of the Banker's algorithm. Then we have learned about use of vectors and what is the reason for using vectors, what does it simplify, right? And then we proceed on with the 6 steps of the Digit-Trans Banker's algorithm, where you have learned in detail the sequence of operations that are performed, and then eventually we moved on to the safety algorithm that tries to determine whether the allocation sequence will lead to a safe state or not, right? So in the next class, what we'll do is we'll take up an example and then we'll try to discuss Digit-Trans Banker's algorithm in a greater detail. Thank you very much. Till then, goodbye.